All right, so let's get to some examples. So we're in chapter 16, talking about confidence intervals. And if you remember from the last video, part 2, when we talk about confidence intervals, we take a sample, and we're in this particular chapter, we're talking about categorical variables, and we get some percent, and we call that percent p hat for our sample proportion. And we were trying to estimate where we think the population proportion P would be relative to where our sample proportion is. And we start with some population proportion P hat. We come out some distance, usually measured in, well, always measured in standard errors, standard deviations. And whatever that distance is, however far you want to come out from P hat, that we'd call that the margin of error. So we're going to do some examples where we find the margin of error. And we had a formula that we looked at last time. So the margin of error is Z star times the standard error of P hat. And standard error, you can think of it like standard deviation. Z star is just going to be however far out we want to go, and it's going to be based on our confidence level. So for this example, we have find the margin of error for a sample size of 1520, 95% confidence. P hat is not given, and so if P hat is not given, we're going to assume that it's 0.5. So we have two parts to this, the Z star and the standard error. So let's talk about Z star first. So to find Z star, we're going to use the normal model. So all of this is assuming that we are based around a normal model. And most of the time we're working with 95% confidence, 90% confidence. Every once in a while we'll see 99%, maybe 98%, maybe go down to 85%. But 95%, 90%, those are the most common ones. And so you probably will do these enough to where you'll memorize the Z star for those two. But it's good to know how to find it. And so the way we find this is we put 0 in the middle. So we're basically working on a standard normal model that we talked about back in chapter 5. And so we have the 0 for the mean, and then we have 1 for the standard deviation. And so basically we want to find the 2 points here where we have 95% in this case between those two. And so we're going to call this, since we're centered at 0, they're going to be the same number. 1 is positive, 1 is negative. And so we're just going to find this one. And depending on your calculator, you may be able to do this directly. If you go on the calculator to the inverse norm, which is what we're going to do, and you have the option for left, center, right. If you pick center, you can just put the 0.95 and then for the area, and then hit center, and it'll give you the Z. But most people don't have that. So when you go to the inverse norm, and again, we did this back in chapter 5, but you go to second vars and pick number 3 for inverse norm on the TI calculator, and it asks for the area to the left. So the area to the left of this Z that we're looking for. So we have 95% from Z down to negative Z, but we also need to get this part. So 95% is in the middle. That leaves 5% on the tails. So we'll have 2.5% over here, 2.5% over here, which we're not really going to use that one. But 95% plus 2.5%, that gives us 0.975 for the area to the left. And then our mean is 0, standard deviation is 1. And when you do that, you get 1.96. So the Z star is 1.96. And whenever we're doing a 95% confidence interval, Z star is 1.96. Now, when we were just kind of introducing this, we used 2 because that's just an approximation. So the 6895 99.7 rule says that within 2 standard deviations will have 95%. That's an approximation. The the more accurate number would be 1.96, which we're still rounding off, but you got to round off somewhere because these are not rational numbers that we're getting. So you got to round off somewhere. We're going to round off at 1.96, which is a little bit more accurate than saying 2. And then standard error or standard deviation of p hat that we talked about last time. Standard deviation, standard error is the square root of p hat times q hat over n. P hat is 0.5, and then the q hat is 1 minus 0.5, which is also 0.5. And then our sample size n is 1520. And then we put that in the calculator, and we should get 0.025 approximately. So that is our margin of error. So if we're at p is 0.5, p hat is 0.5, then we're going to add 0.025. So this would be 0.525 over here. Subtract 0.025, so that'd be 0.475 over here. And so the 0.475 to 0.525, that would give us our confidence interval. But in this case, it's just asking for the margin of error, so that's all we need to find. All right, now find the margin of error for 90% confidence. And so it's going to be the same thing. Standard error, of course, is not changing because we're still using the p hat from the last example. So the only thing that's changing now is the z star. And so you can do the same thing that we did on the last one. 0 goes in the middle, and now we're going to find negative z star and z star so that 90% is between these two. And if 90% is between these two, that leaves 10% in the tails. Half of the 10% is over here. Half of the 10% is over here. And so z star, we're going to do inverse norm again. Now the area to the left of z star would be 90 plus 5. So that's 0.95, 0, 1, and we get 1.645. And again, 90% comes up a lot. And so probably you can memorize the z star for 90% confidence is 1.645. So we have 1.645 times the square root of our p hat is 0.5, our q hat is 0.5, and our n is still 1520. And when we do that, now we get 0.021. And this makes sense because we said at the end of the last video that if you increase your confidence, the margin of error will go up. If you decrease the confidence, the margin of error will go down. And so we can see we decreased the confidence from this example, 95%, down to 90%, and the margin of error did go down. And the reason you can see from the formula, in this one up here, we're multiplying by standard error is not changing because p hat is not changing, the n is not changing. The only thing that's changing is the z star. And so the z star is going to go down, which means this product will go down. So it makes sense that as z star goes up or down, margin of error is going to go up or down in the same way. All right, so assumptions and conditions again. These are the same as what we looked at in the first video in this chapter. Independence, assumption, and randomization. 10% condition. Again, your sample should be less than 10% of the population, and then success failure condition. N times p hat should be greater than or equal to 10. N times q hat should be greater than or equal to 10. So these are the same as what we saw when we were looking at the sampling distributions. The only difference is now we don't know p, so we're using p hat, but same idea. All right, so next example, what sample size do we need to survey in order to have a margin of error less than 3% at 95% confidence? So what sample size? So that means we're looking for n. So we have our margin of error formula. So z star, and I'll go ahead and fill in the standard error formula. And so we're looking for n. So we know everything else. The margin of error is 0.03. And we could, so less than, so we could say less than, but we'll just say equal because it doesn't matter. We're going to do the same thing anyway. So Z star for 95%, like we saw a minute ago, that is 1.96. And P hat is 0.5, Q hat is 0.5. And now we're looking for N. And so we need to solve this equation for N. And probably, as far as this class goes, this is probably the most involved algebra that we do. And there's nothing too complex here. And we're always looking for the same, anytime we have an algebraic type problem in this chapter, we're looking for the sample size. The steps are the same every time. And so if you have trouble with the algebra, you can literally memorize the steps. So it's not so much as figuring out what to do, and we're doing different things based on the problem. These problems where we're looking for the sample size are all the same. So first, we're going to isolate the square root part. And so we divide by the 1.96. Now, one thing you got to be careful of doing these is you got to be careful with the rounding. It's very easy to say, so the answer is 0.015306. Now, if you put 0.02, you're going to be way off on your final answer. So I always recommend at least 6 digits, although as you're calculating this, you really don't have to retype the answer. You can keep using the same answer. Just hit second and the negative, which brings up the answer that you just calculated. And so that way you don't have the rounding errors. We'll go ahead and multiply the 0.5 times 0.5. And so we have 0.015306 equals the square root of 0.25 over n. Now that we have the square root by itself, we can square both sides. So square that. And so now I'm just going to hit the square button on the calculator, and it's going to calculate that. It'll automatically calculate this whole number, not just the 6 digits. So we put, although it doesn't matter, if you just type in 0.015306 and then square it, you're not going to have issues. Now, on my calculator, we get 2.3427 string digits, and then at the end it says E-4. Now, what the E-4 means, and you'll probably see this a little bit more as we move through these next chapters, the E-4 just means it's scientific notation. So this is 2.34, etc., times 10 to the -4. So we need to move the decimal 3 places to the left. And so that is going to be 0.0002343. So 234,277, we'll just round that to the 3 there. Now on this side, the square root goes away. And so we equals 0.25 over n. All right, so let's go back up here. And so now we can cross multiply. Now it's a fairly easy algebra problem to do. We'll divide by that number. Oh, shoot. Crap. Just ignore that box, I guess. And so then we get 1067.1. Now, this is a sample size, and typically sample sizes or samples, even if we're not talking about people, typically we can only have our sample size 1 or 2 or 3 or 4 or 5 or whatever integer. Cannot have a 0.1. So now where you got to be careful, or at least make note of, you always round up on these. So even though it's a 0.1, we're going to round up. Now, the reason you round up is we want the margin of error to be less than 3%. If you rounded down, which typically you would, if 0.1, you would round down to 1067. So try plug in 1067 for the n. Keep that at 1.96. P and Q are 0.5 each. And if you do that, you will not get, let's see what we get. You will not get less than 3%. You get 0.030001,562. So the margin of error at 1067 is not less than 3%, which is what we're looking for. But if you do 1068, then you get 0.0299875, which is less than 3%. So the reason you always round up is because this gives you exactly 3%. And if you go down, the denominator goes down, this fraction gets bigger, and so you're not less than 3%. You need the denominator to be bigger than this, and that gives you less than 3%. Okay, so, again, do these over and over again, and the process, these steps become pretty easy to remember the process. So always divide by the z, square both sides, and then essentially this decimal and the n are switching places. So you cross multiply, you get the n over there, and then you divide by that, and so you have n over, or n equals 0.25 over that number, and there's your answer. All right. So we'll go ahead and stop this one, just to keep it from being too long, and we'll pick it up on the next one.